Rutherford is known as Ernest. Okay. Ernest Rutherford wanted to further explore the nature of the atom, but he was also messing with radiation. And he was dealing with things called alpha particles. Ernest Rutherford dealt with alpha particle. Okay, and what you need to know about an alpha particle right now is that it was very dense. Very small. Very fast. Okay, and positively charged. Okay, had a plus charge. These are the properties of an alpha particle. And he was able to send beams of alpha particles. He knew that alpha particles came from uranium. Okay, which is, you know, an element that we, okay, it's the largest, has the largest atomic number of any naturally occurring element. We'll get more into that in the near future. But this uranium would give off alpha particles. He knew it gave off alpha particles, and so he was able to contain the uranium inside of a lead box and cause alpha particles to only come out through a hole in the lead box. And so he was essentially creating a beam of alpha particles, not a laser. It was just a straight line beam of alpha particles that were shooting out of the uranium. Now, he would start hitting things with these alpha particles. Okay, things like other elements, and he was finding that these alpha particles were shooting straight through, and so, okay, he took another very dense element called gold and pounded it into really thin sheets. Okay. And inside each of those, so here's our series of gold atoms, and from our understanding of the Thomson model, inside there were these electrons, right? Right? So inside the gold atoms we have these electrons. So this is, mind you, this is Rutherford dealing with the previous model of the atom. You guys follow me there? Okay. And he was shooting an alpha particle at it. Pew, pew. All right. Right. No. It's not a laser. Okay. So he would shoot a beam of alpha particles at it, and then he found that behind it he would put a phosphorescent screen and these alpha particles in general would shoot right through and make a pretty steady dot on this phosphorescent screen. Now remember, the phosphorescent screen, this is the same idea that Thomson had inside the cathode ray tube, right? And that he was shooting electrons and it spread across the screen and it made this streak across the screen. It's the same material, that if it's hit by a high energy particle, it lights up. So, particle comes through, hits the dot, there would be like a little cloud around it. Okay, a little less dense, so it'd be really dark in the middle and less dense as it expanded. And then he'd see some occasionally way out here, and he hypothesized at the time that that's just because of the negative particles, the negative electrons in the atoms would give a little tug to the alpha particles coming through, and it would deflect them off the regular course. And it was very rare that they would get close enough to electrons, and so that's why it wasn't very dense out here. Does that make sense to you guys? Okay, because like charges attract each other, and so they would deflect kind of mildly as they passed through. But it was enough to make him think, well, what about the ones that I'm not catching on the screen? And so he needed to make a comprehensive test about this. And so he set up the gold foil experiment. Dun, dun, dun. That's right. Okay, so we have Rutherford's. Okay, Rutherford's gold foil experiment and traveling shell. I'm kidding. He didn't really travel with it. I'm just making you write funny things in your notes. Okay. So we talked about this lead box that he had. So he would have this. Okay, and inside, I need to get really fine here, so. Inside here, we have this lump of uranium, right? And the uranium would give us, so that this is a cutaway view of inside the box, right? See that? Isn't that cool? Yeah. Okay, so out of the box, this is how he did it. So there's uranium inside the box, and out of the box, and this whole thing is lead. Okay, and this is a lead. Okay, so lead box, PB is the symbol for lead. And out of the lead box, shot an alpha particle. Just a minute here. It's an alpha, and I will show you how to draw that in just a moment. Oh, no. There, shoot, I screwed that up. I will get this drawing right one of these days. All right, although those shouldn't be overlapping. I shouldn't be able to see both sides of the board. All right. Oh! How's that? Okay, so the alpha particle shoot in. Okay, and it would either, and what mostly happened was that it would pass through the gold foil and make our dot, right? Because that was similar to what was going on over here, right? We'd have this dot with a little cloud around it, which means we had most of our most of our alpha particles were in this little spray around the center line of the beam. Yeah. And then as we'd move away, it'd get a little bit less, a little more fuzzy as we go away until eventually it'd disappear. Okay. Now, but here's the catcher. Because he put detectors, and here's why it was such a brilliant experiment. Because he put detectors behind the screen, he was able to detect the ones that did that. And this is the important one. In this range right in here was 98% of all of the particles. 98% of the alpha particles went straight through, were not affected whatsoever. Okay. Other way, this is. Okay. I've got my screen right here, so I'll fix it. Just point out that I can't see it, and I'll fix it. 2%. Okay, less than 2%. Okay, was in this range. And this guy way over here was about 0.01%, okay, of all of the particles bouncing back. These were the results of the experiment. Okay, this is the data that he returned from his experiment. What does this tell us? Okay, so remember, our alpha particle, if you go back to the top of our notes, our alpha particle was very dense, very small, very fast, and had a positive charge. Yeah? Okay, think of this as a subatomic bullet. What is it going to take to make a bullet bounce back from the gold foil? Okay, what's that? Higher density or just very high density, right? Something of comparable density is going to make it push back. That was his first conclusion. Okay, so that's the next part of these notes up here. So I'm going to put them up here. Okay, that's the first one. There must be something dense in there. You guys. There must be something dense in there. Okay, don't know what it is, but there's got to be something dense because otherwise it's causing. Otherwise everything be going through. There has to be something dense that's causing the alpha particle to bounce back. Okay, not only must there be something dense in there. In fact, so we can get the whole page here. What does this tell you? That if it's 1/100% of all of the alpha particles are bouncing back. Give me more. I'll tell you that it's about the same density. He was able to determine it was about the same density as the alpha particle itself. Why would there only be 0.001% actually bouncing back? How often was an alpha particle hitting something of that density? Every time? Well, this is actually 10,000. Right, this is 1 out of every 10,000. So what can you tell me about the thing that it's hitting?
It's very small.
What's that?
It's very small.
It's really small. the dense thing must be very small. Oh, wait a second, that kind of looks like these, huh? The dense thing has to be very small. Why? Because of the 1/100th of a percent is actually bouncing back. Okay. What else? What's that? It's going really fast. We can't really tell that about what's going on in the gold foil. We know the particle is going very fast, but the gold foil, it's not really going anywhere.
Oh, since it's reflecting off of it, then they must be the same because the opposites attract in the same reflect.
Oh, there's something to that. What about these guys that are coming over here? Because we're
Hitting it.
okay, they're not hitting it, but they're deflecting a pretty significant amount, right?
Yeah.
Okay, so if all the stuff has the same mass, but we know that there's a really dense part to it, most of that mass is going to be in that dense part. Does that make sense? So the mass doesn't change; it's still the same mass, but all that mass that used to be here, okay, is now concentrated into a little dense thing. So that leaves what based on the size of the atom?
Small.
Ooh. If all of this, right? We had our Thomson. We had Thomson with all that, right? Okay, and now all of this mass up here is now there. Or actually, I should do it with the other color. Is now there, and we have that, right? Does that make sense? That we took all the mass of the atom and shrunk it down to a really teeny tiny point. Okay, what's the charge on that?
Positive.
Okay, it's positive. Okay, the dense thing okay, it must have a positive charge because we already know what the negative charge is, right? The negative charge is from the electron, so it's got to have a positive charge. Okay, and the fourth one, which we kind of implied right here, the atom okay, the atom, however, is still the same size as before. The gold didn't get smaller all of a sudden. It just concentrated its mass. Okay, these four things came up with, he put these all together and came up with one conclusion. Okay, one final, this is what we've discovered about the atom. Positively. Okay, and he discovered the nucleus. That is the importance of this particular experiment. Yes? Okay, so the tiny, dense, positively charged mass in an atom is logically at its center, and it's called the nucleus. He called it the nucleus. similar to how cells have nuclei. Okay, because that was the center of the cell, so we call the center of the atom the nucleus of the atom. Okay, and so now we have the Rutherford model of the atom, and at the center is this tiny positively charged particle. Okay, and so I've been staying consistent. So if it's got this gold look to it, it's got the positive charge, and then around it are the electrons that are moving around the nucleus. Okay, and there might be some inside of this, but it's out here. In fact, let's draw some inside. Okay, so now we still have the same size of the atom, but now we have all of the mass concentrated at the center. Okay, the positive charge and the mass are concentrated at the center of the atom. Okay, and around it, the size of the atom and the size of the atom was determined by the distribution of electrons spread out through the whole thing. Okay. All right. That is the Rutherford model of the atom. So we'll stop there, and this is part 2 of the lecture.